So last time we introduced the ideal gas model, we covered a lot of basics, but I didn't cover enough applications. You can either do the change in entropy for an ideal gas mixture on a molar basis or a mass basis. So with the mass basis, you'd have the sum of the masses of the individual species times the change in the entropy, let's say S2, S1, or on a molar basis, the change, we have the sum of the number of moles, and we have S bar 2 minus S bar 1 of I, so sum over all the components. What's again that bar mean? It's on a molar basis. That's the notation for this book, that the bar over a U, let's say U bar, or over an H, or over an R, it's all on a molar basis. Okay, so this change in entropy would be something like C sub P, natural log of final temperature over the initial temperature, minus R, natural log of the pressure final over the initial pressure, or first pressure, inlet pressure, something like that, and it would be for that component, 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 for that component. So definitely the C sub P for that component makes sense. Definitely the R for that component makes sense, and we recall R is R bar divided by the molar mass of that component. All right. Definitely, let's take a look at this. Does the final partial temperature make sense? No, there's no partial temperature concept. So there's no temperature associated with component I different than the component J, or first component different. So we get rid of that. No, it's just the final temperature over the. But let's look at pressure. Do we have something like the final pressure, at state 2 for component I? Yeah, we sure do, don't we? And so that stays, and what we find is that turns into something like the mole fraction of I at the final state times the total pressure at the final state. And then you have the mole fraction of at the initial state of I times the initial pressure, and that's the natural log right there. So this component comes down. Does that make sense that you're using the Y's and the P's? But is there any Y's times T's? Again, this is any Y's times the T's? No. No partial temperatures. Okay.
Wouldn't the Y's be the same until they cancel out?
They do when you have one inlet, one outlet, let's say going through a compressor or a closed system that's only being compressed. But if you could have a closed system, I can make it a problem where I have a closed system analysis where I have a container like this and a valve and a container, and this starts with argon and this starts with nitrogen, and that'll be a closed system analysis, and I have to be careful there. And the other one where I have to be careful is I mix the two streams, nitrogen and argon, to come out with the mixture. But a lot of times, let's say I have a mixture of nitrogen and argon, and they go through a pump or a compressor, a nozzle, a diffuser, a turbine. It didn't change the makeup. The mole fraction's the same. Or if I have a piston cylinder apparatus and I do something where I don't know, heat it and put a egg beater in there, and I have work and all that, but I'm not changing, so you have to really pay attention to the problem. All right. You could also do this on a molar basis. It looks very similar. Let me see if I can write it down. CP bar. Hey, what's that bar over that C sub P for? Molar basis, that's right. So what's the relationship between C sub P bar and C sub P? Let me do a little quick here. What are the units, SI units for C sub P, the specific heat? Kilojoules per kilogram Kelvin. So what do I do? Do I multiply by molar mass or divide by molar mass? So if I divide by molar mass, I'll take a look. The C sub P bar, that'd be kilojoules per kilomole Kelvin. and a molar mass, kilogram per kilomole. So whoever had said divide by is absolutely correct, because the kilomoles cancel and we're left with kilojoules per kilogram Kelvin. All right. So we have, I'm trying to finish this equation, we have C sub P bar natural log of T2 over T1 minus R bar. Do I need to put a subscript on that and say, oh, it's for the ith component, R bar subscript I? No, that's the universal gas constant. Very good. Natural log, and here again we would have the y at the 2I times P2 and the y 1I times P1. And then you'd have times the number of moles and then do the sum. Just like this was times the amount and do the sum. Okay. Where's the mass fraction? These right here?
Like on the left side.
This would be the mass of that entity. Yeah. Now, let's say I want to do something like this where I'm doing a mass flow rate through. It could be an m dot. And then I'm not doing a sigma, but I'm doing a sigma dot. But as I'm looking at it right here, I'm just doing the change in the entropy. Okay, so yeah, it would be just the mass. Okay. That's a good thing to review. Everything's pretty simple except for the change in the entropy for ideal gas mixtures. So we solved this problem. So a gas mixture having a molar analysis of 70% carbon dioxide and 30% hydrogen. It enters an insulated compressor operating at steady state. They give you the inlet pressure, inlet temperature, and a mass flow rate. Now, right away, you can see, like, okay, they're giving me a molar analysis for the makeup, but they're giving me a mass flow rate. You're going to have to go back and forth between the two. Okay? They could have given you a molar flow rate. And it's compressed to a final pressure of 1,500 kilopascal. The kinetic and potential energy effects are negligible. The isentropic compressor efficiency is 80%. And they want you to calculate the exit temperature and the power required to run the compressor, and the rate of entropy production here is a sigma dot rate of entropy production around that compressor. Here are the properties. Use that value of C sub P and C sub V for carbon dioxide and for hydrogen. First of all, before we do it for an ideal gas mixture, just do it for an ideal gas. If I just had a compressor and I have an ideal gas, a pure ideal gas going through it, we could answer all these questions, couldn't we? And so just do a quick review of that type of problem. We would say, this is inlet state 1, outlet state 2. Oh, I would calculate 2S. And that 2S would be T1, because you've done it so many times. It'd be P2 over P1 raised to the K minus 1 over K for isentropic compression of an ideal gas over a pressure ratio. Look good? And then you'd say, so the isentropic efficiency gives me an actual T2 actual, which will be T1 plus 1 over the isentropic compressor efficiency times T2S minus T1. Does that strike a chord? Does that look good? So there you go. So now you say to yourself, if I have a mixture, what changes? Somebody says, I'm your magic genie. I'll answer all your questions. Well, I'd like to know what is K of the mixture. Because if I knew K of the mixture, I would just use the same equations, wouldn't I? So how do I get K of the mixture? C sub P of the mixture divided by C sub V of the mixture. If I do it on a mass basis, that's great. If I do C sub P bar of the mixture divided by C sub V bar of the mixture, will that work? Will that give me the same K? Yeah, you could work on a mass basis or molar basis. Either one will work. So conceptually, I need to get C sub P bar C sub V bar or C sub V and C sub P. And, okay. I would get T2 pretty rapidly. How about once I get T2, how do I get W dot C? The answer for part B? Yeah, we'll just do a little control volume, energy balance around it. It's equal to the mass flow rate of the mixture times the specific heat constant pressure of the mixture times that T2 actual minus T1. And somebody says, well, how about if I do the molar flow rate times C sub P bar of the mixture times T2 actual minus T1. That'll work too. Why don't I do the molar flow rate of the component, let's say I, C sub P I bar, T2 actual minus T1, and then sum over the two components? Will that work? Sure will. There's a couple ways to do this. Let's say you solved for part A and part B. How do I calculate sigma dot? All right. Well, where did this equation come from? I did a control volume analysis around the compressor. I did the first law of thermodynamics. Now I'm going to use the same control volume. I'm going to do the second law. What is the equation that will come out? True. Or you could write it as N dot times S2 minus S1 bar. Or you could sum over the N dots, and it's very similar. Let me finish it out. S2 bar minus S1 bar of I. You could also put it like the mass flow rate of each component times S2 minus S1 of each component. So which form do you think, version A, B, C, or D, do you want to do? Just so I can kind of finish it out. A? Okay. Or B? B, because if I had to get the C sub P of the mixture and to get the K, then let's just use it. So let's just finish it out with B. So we have the given mass flow rate. We know it right there. And then we're going to have C sub P of the mixture, natural log T2 actual over T1. And then minus, now this is a little tricky right here, R bar divided by the molar mass of the mixture. So somewhere along the line, when you get C sub P of the mixture, go ahead and get the molar mass of the mixture. It's really not that hard. Isn't it the sum of the mole fractions times individual molar masses? Sure is. So let's go ahead and know that we're going to put sometimes I'll emphasize and I'll put that this is of the mixture or of the mixture, but I do believe the book just says without a subscript, that means it's for the mixture. And let's finish out this equation. We have the natural log, and now we have the case where we have the y of and the partial pressures, but you know what? They just cancel because the composition didn't change. Each of those terms has the same mole fraction. Okay? So it turns out to be the ratio of the change in the pressure. Look good? Well, here's the solution in Excel. I like, even on your exams, and recommend you set it up in a table to help organize things. So right away, list your gases. There's only 2 of them. List their molar masses. I didn't put up in here the header, the value, but that's kilograms per kilomole. Get the mole fraction from the problem statement. Do the multiplication of y times m. When I sum that, what do I get? That's the molar mass of the mixture, isn't it? Yeah. I can calculate the mass fractions. The mass fraction would be this 30 divided by this 31. Okay, and then this value divided by that value gives you. So it's very little, even though it's 30% by volume or by mole fraction, it's 30% hydrogen. It's only 2% by mass hydrogen. Hydrogen's so light. And put in the specific heats of each component, mass fraction times the specific heat, add them together. Guess what that is? The specific heat of the mixture. Do the same thing for the C sub V's. C sub V of the mixture. If I want, I calculate that ratio of these two entities. That gives me the K of the mixture. Here I'm just repeating. Here, this one's copied down, and copied down. So we come in with the inlet temperature to go from T1 to T2S. That's just going to be T1 times P2 over P1. I'm repeating myself, but K minus 1 over K. And then you use efficiency. They wanted to answer in degrees C, take off 273. Here is the mass flow rate. Here's the equation I used, just typed it out. Same thing for the entropy generation. Does it look good? Ready to press forward? Did I solve it too fast or too slow? Is it okay? If I go too fast, what happens? You don't follow, you get lost, but hopefully you followed, right? All right. Here's a mixing problem. I mentioned it. I've outlined the steps on the mixing problem. Do you want me to solve it in detail or do it like I did the last problem? Is that fine? Okay, I'll do it like the last problem. So we have nitrogen and some information about the nitrogen, the temperature coming in of the nitrogen, the volumetric flow rate, so temperature, pressure, and volumetric flow rate. I use the symbol AV. That's, I think, consistent with the book. Maybe in your fluids book, maybe use another symbol. Hoot has taken fluids. What symbol have they sometimes used for volumetric flow rate in fluids? Q. That's exactly right. But in our textbook, what's Q? Heat transfer. So we got to watch out for the collision of symbols. All right. And then they also have an argon fluid stream, and it has an inlet temperature and an inlet pressure and an inlet volumetric flow rate. And then it comes out at this final exit pressure. Now, what's interesting is all the pressures are the same, which makes sense. There's no pressure gain or pressure drop. It's just mixing. All right? All right. Now, let's do this. What are they asking us to calculate? The mixture temperature. Is it this temperature coming out? Yeah. Okay, so it comes in, the nitrogen comes in at 40 degrees C, and the argon comes in at 110 degrees C. If you just had to take a wild guess, what temperature would you just take a wild guess is what is the temperature of the outlet? About 75. You add 40 and 110, you get 150, divide by 2, at about 75. Now you're starting to pay attention. Well, look at the volumetric flow rates. It looks like there's a lot more nitrogen. Well, if there was a lot more nitrogen, would it come in higher than 75 or lower than 75? Lower. Maybe it's going to come out 60 or 70 F. There's really good insight because sometimes we make little silly errors and then we want to be able to check ourselves. All right. So, how do I calculate that temperature? Introduce what am I doing? Introducing a control volume and apply which law? First law of thermodynamics. And even though it's a mixture, you probably want to think, how would I apply that first law without it being a mixture? It would be something like the mass flow rate coming in here. Maybe I want to call this state 1. State 2, state 3 is my outlet. And I know the notation gets a little cumbersome, but you would have something like the mass flow rate at 1 times the enthalpy in at 1 plus the mass flow rate in at 2 times the enthalpy in at 2 is equal to the mass flow rate out at 3 times the enthalpy out at 3. True or false? True. Okay. But we see that this mass flow rate at 1 is only nitrogen. This mass flow rate at 2 is only argon. The mass flow rate out at 3 is a combination of the nitrogen and the argon, isn't it? So I'm going to just substitute right there, and I'll have this H3 here, and this is H2, and this is H1. And I can rewrite this equation something like the mass flow rate of the nitrogen, well, maybe I'll write it like this. Argon first times enthalpy 2 minus enthalpy 3 of the argon minus, is equal to the mass flow rate of the nitrogen. Enthalpy, I'm looking at my numbers again, I have erased that one. This is 1 up here, right? Enthalpy 3 minus enthalpy 1 of the nitrogen. It's like what comes out of the hot went into the cold. It's as if this stream right here just had a heat transfer with that stream right there, and the outlet of the hot stream and the outlet of the colder stream have the same temperature. That equation look okay?
Are you kind of treating it like a closed bead water heater?
Yeah. Yeah. But here what I have to do is I have to say, well, that hot stream is all argon and the cold stream is all nitrogen. Okay, just for the energy balance. Now when we get to part B, oh well, I have to deal with the mole fractions in the outlet. So I could also write this as the molar flow rate of the argon times, I'm going to put it as, well, do it in a couple steps. The mass flow rate, the specific heat, constant pressure, T2 minus T3. And notice, we only have this, we have the same outlet temperature of the mixture, so it doesn't make sense to say T3 of the argon and T3 of the nitrogen. They're the same temperature. All right. Equal to the mass flow rate, I needed to put argon right there, of the nitrogen times the specific heat constant pressure of the nitrogen, T3 minus T1, right? I'm looking for T3. At this point, T3 is equal to, it's going to be mass flow rate specific heat of the argon times the temperature of the argon coming in, which is T2, plus the mass flow rate specific heat of the nitrogen times the inlet temperature of the nitrogen, T1, divided by the mass flow rate specific heat of the argon plus the mass flow rate specific heat of the nitrogen. You get a very similar equation that you've seen. Hopefully you've seen this pattern before. Oh, I'm mixing. I'm getting a final average temperature. Somebody says, oh, I like to work in molar flow rates. No problem. The molar flow rate times Cp bar for the argon times the inlet temperature of the argon plus the molar flow rate times the Cp bar of the nitrogen times the inlet temperature of the nitrogen divided by n dot C sub p bar of the argon plus n dot C sub p bar for the nitrogen. Hopefully I'm not too, being too... The next slide will have the numbers, okay? Give me a thumbs up if you followed that. You're good? Do you need more time to think about it? All right, you're good? All right, now the hard part, part B. Well, how do we calculate the rate of entropy production? Just the general approach is control volume, same control volume we used for the first law to calculate the outlet temperature, and we do the second law of thermodynamics. So, what do I do here because I ran out of room? How about if I scroll down? Or should I go to another page? Just scroll down a little? All right. So if I do that, I have to be able to write the second law of thermodynamics as if they're just two streams first, and if I got that correct, then I can put it in for an ideal gas mixtures. So wouldn't the rate of entropy production in that control volume be, you want to do it on a mass basis or molar basis? Mass, okay. So we'll do the mass flow rate of the inlet argon. Was this my argon? Yeah, that's my argon. Maybe I'll do the nitrogen first. Okay, times, what we're doing here is we're just going to say we're going to change the entropy S coming out, which is 3, minus S coming in, which is 1 of the nitrogen. And we're going to add to it the mass flow rate of the argon times the specific entropy going out of the argon. That's S3 of the argon. And this is argon here. But because I put the nitrogen here, I don't need to really put it on both of those terms. Minus S2 of the argon. I pause. I stop. Does that equation look good to you? Before I start worrying about partial pressures and that, does it look okay? Now we can focus the mass flow rate of the nitrogen. Let's expand it out. C sub P, natural log T3 over T1 minus, I'm going to put R bar divided by the molar mass of the nitrogen, natural log, and then I'm going to have the mole fraction of the nitrogen going out. So that's either way, I don't have a preference, like do I put Y3 then N2 or do I put YN2 comma 3? To me it doesn't matter. All right. If I was the editor of a book, I would pick one and stay with it. But I think you understand that notation. And then we multiply by P3. That would be the partial pressure of the nitrogen outlet at state 3. And then here we're going to have mole fraction of, at state 1, nitrogen times the pressure 1. Before I move to the next term, give me a thumbs up if you agree. Does anybody have a question? Like, is that syntax right? Is that subscript right? Because I could easily make an error. Can we cancel these two pressures? Can we cancel the mole fractions? Nope. One of those mole fractions is really easy. Which mole fraction is? That's right, it's 100%. It's pure nitrogen coming in at state 1. That's right. Okay. So now let's finish out for the next one. So we're going to have the mass flow rate of the argon times the C sub P of the argon, natural log of T3 over T2 minus R bar over the molar mass of the argon, natural log, and then we have the mole fraction going out of the argon, P3 divided by the mole fraction coming in of the argon, P2. And those pressures cancel likewise. Okay. Somebody says, it looks like this problem is solved. True? I mean, how am I going to get the mass flow rate of the nitrogen? Well, I would probably go and I'd say I had the mass flow rate of the total mixture, 2.5 kilograms per second, and I'd multiply by the mass fraction of the nitrogen coming in. Oh, come on, hold it. Back up here. Let me look at my problem again. They didn't give me the 2.5 kilograms. I'm still thinking about the previous problem. They gave me the volumetric flow rate of the nitrogen coming in. True? So the mass flow rate of the nitrogen coming in is equal to the volumetric flow rate of the nitrogen at state 1 times 1 over the density of the nitrogen. And how am I going to calculate that mass density? The ideal gas equation. You're right. And so the ideal gas equation is that we have the pressure coming in at state 1 equal to the density of the nitrogen at state 1 times the gas constant R bar divided by the molar mass of the nitrogen temperature. Do you like that equation? No? You don't like it? All right, tell me what's wrong with it. I'm sorry, which one? Oh, you could write it as PV is equal to RT, and then the reciprocal of V, so I'll put the P1 is equal to rho RT, or I'll put that the P1 molar mass of the nitrogen equal to rho RT. There's so many. I need the rho. It's the pressure at 1, which is just pure nitrogen, times the molar mass of nitrogen divided by the R bar, and that's an R bar right there, and then T. Now you like it? Okay, good. That's how you get the mass flow rate. How about down here for the argon? Same thing. Okay, good. I have numbers on the next slide. But here is a rub right here that I need to get to. How do I get the C sub P of the nitrogen? You're saying no problem. I think I'll look it up around the average temperature of maybe 75 degrees C, no problem, out of the appendix. But what about the C sub P of the argon? Oh, do you have a comment or question?
Would you just use 300 Kelvin?
Yeah, I would. I would. Definitely. But if you wanted to, you take the 75-ish, you add to 273, and then you have to iterate to get a really better answer. But okay, well, how about the C sub P now of the argon? Same thing. I'll go right into my appendix. I look at table. Who has an appendix on them? Okay, can you look up and tell me what table do you get C sub P for the nitrogen out of? And then the hard one, that's where I'm getting to, for the argon. And some people, I think, already know where I'm going on this. Because this will happen. The students will be like, you gave me a gas that I cannot find the C sub P from out of this appendix. That's what I'm covering right now. The nitrogen, no problem. What table are you in? Table A20. Table A20. 20, just A20. And let's pick it off at 300 degrees C. For the nitrogen, I'd say C sub P is about 1.039 kilojoules per kilogram Kelvin. Hey, that's a great table. A20 has air in it. It has nitrogen in it, has oxygen in it, has carbon dioxide in it, has carbon monoxide in it. It has hydrogen in it. Does it have argon in it? Oh, too bad, right? So we look for another table or something. Somebody already knows where I'm going. You're going to go to table A. You're absolutely correct. A21. Somebody says, I don't see argon in table A21. Where is it at? Monoatomic, and it's in the footnote. And so in table A21, you find that they gave C sub P bar divided by R bar is equal to alpha, which is 2.5 for all of the monoatomic gases. For argon, for helium, for neon, if you ever use neon, right? I mean, really just going to use argon and helium is the most common. But anyway, so somebody says, well, I don't need C sub P bar, I need C sub P. But the question is that equal to C sub P divided by R? Take the bars off of both of them. Is that true? It is definitely true. And so if you're looking for C sub P, it's 2.5, which is 5 halves of R, or 2.5 of R bar divided by the molar mass of that monoatomic gas. There's a few steps there. Once you've done it once or twice, you know it. I wish the book would have given you a table that had argon. I mean, it's not going to take up much more space. Look at all the white space right below here. Plenty of space. But they didn't. Right? So there you go. That's how you get the value of C sub P. I think the rest of it's easy. Let me show you some numbers. So here are the numbers. Looks like I solved it in molar flow rates. And I converted over to C sub P bars. And I actually calculated the mole fractions. And we get the final temperature and the final entropy generation rate. Sound good? Very good. Any questions? And we're going to check out of that. And we're going to move over to now talk a little bit about psychrometrics. What is psychrometrics all about? Well, if you're like me, I use the dictionary to get the correct spelling, get a little understanding, and right away they say something, Wikipedia says something about not to be confused with. So I'm sure a few of you were thinking about the 1960 slasher thriller. I have no idea. I've never seen this movie, Psycho, but it's a movie. Don't be confused. We're going to not study movies, nor are we going to study TV shows. Psych, which aired between 2008 and 2014. I have never seen either of these, but we're studying something that can be easily confused, right? Like some student will say, I need the psych chart. And somebody's, using a little slang, like, what, you got some confused, mentally confused chart? What do you got? It's a study of moist air. All right. So we're going to be studying different temperatures, talk about humidities, talk about how to get properties for moist air, etc. So let's just jump right into it. First of all, there's three types of airs: dry, moist, saturated. Dry air. What do you think they're talking about when they say dry air? This is not a hard question. This is the easy one. No water vapor in it. Are you, right now, is the room air in this room right now, is it dry? No, there's humidity in it. So the dry air we'll just say is dA, and I'll use that like, oh, it's dry air. And I'll talk about the density of dry air, and I'll talk about the molar mass of dry air, etc. The molar mass of dry air is 28.97. That's what the molar mass of dry air is, right? Kilograms per kilomole. Okay, then you have moist air. Well, that's what we're breathing, moist air in this room. What's the difference? You have some water vapor in it. So it's dry air plus water vapor. And right away the partial pressure concept comes in. The total pressure of the air in this room is, if you can make it up as the sum of the dry air contribution, the partial pressure attributed to the dry air, plus the partial pressure due to the water vapor. Somebody says, Professor, I learned that the dry air is made up of nitrogen, oxygen, argon, carbon dioxide. That person over there just belched or did something else. I think now there's some methane in this room. It's all lumped together, okay? It's all lumped together. We're just going to talk dry air. All right. Now the next concept is saturated air. This is not hard, but it's stressing you a little bit. What do you know about saturated air? It has the maximum amount of water vapor in it. What happens when you have a little bit more than the maximum? It'll dew out. It will dew out, right? It can't hold it. It'll condense. It'll actually turn sometimes into a fog. You'll see the water droplets like little white things that'll block up your vision, not as transparent. Okay? But this is now saturated. So the key is the pressure of the water vapor that's in the air reaches some sort of maximum. Well, what value is that maximum partial pressure of water vapor in the air? Well, when would it be maximum? I mean, And you know what? Your study of thermodynamics comes in so handy. Because in this appendix, in the first real table, not table A1, but table A2, you saw table A2, you saw a bunch of temperature values, and the next column over is the saturation pressure. And so right away, the maximum, let's say I come down here and I look at 20 degrees C, and then I read over and I say, oh, what is P sat? That's the saturation pressure. That's the maximum partial pressure that water could exert in my moist air. When it exerts that, it's saturated air. Oh, somebody looks down here, they say 25 degrees C. You know what? It's a larger value. Do you know when the air gets hot? Guess what? It can hold a ton of water, or a lot of water, something like that. You know what I mean? It can hold more water vapor. A lot of water vapor and hot. How many people have been, after a rain shower in Houston or somewhere in Galveston, and you could just feel it, right? And it's like still 95, and it's really humid. Or New Orleans, or somewhere in Louisiana, right? Yeah. And so what you find, though, is when it's really, really cold, guess what? Even if it's saturated air, there's not a lot of moisture in it, is it? How many people been up north where there's a long winter, right? And then you start to get dry skin, or you walk across a carpet and touch something like the knob on a door and you get shocked because of the dryness. You have less static electricity. Or even me, I'll get nosebleeds because it dries out the passageways in the nose. Anybody? Or they say, don't run outside because it'll scorch your lungs. It's so cold. Because of the cold, you can't take deep breaths. It's so cold it can hurt your lungs. Anyway, it's very, very, very dry, even if the air is saturated with moisture, because it can't hold much when it's cold. So those are 3 degrees of air: dry air, moist air, saturated air. We also have corresponding temperatures. What's the dry bulb temperature? It makes sense. You look at a thermometer, that bulb at the end is your temperature sensing unit, and guess what? It's dry. Well, then they have another one called the wet bulb temperature. Well, let me just try and describe it. I had a sling psychrometer that I did bring into the room for a few years. Last year, I think I brought it in, and after it had circulated, I think somebody whacked their friend with it in the head or something because it came back broke. So I can't pass it around. But in this sling psychrometer, you have 2 bulbs, 2 thermometers, right? And one you leave on this side without a sock on it. A little sock goes on the other one, a little wicking material. And it goes into a little cap that you could take off and fill with water, around room temperature water. Or let it sit in the room for a while so that you don't fill it with cold water or hot water. You fill it with room temperature water, and the sock all is wet because it's wicking up in the sock from your reservoir. And then you sling it around in the room. Oh, it's fun. Students like to do it, and then they like to get close to their friend's head, and I think that's what happened to my bulb. But luckily, it wasn't a mercury-filled thermometer. They make them with red dye. I didn't have to call out the EPA. It's probably spilled somewhere on their shirt or something, or on the seat you're sitting in. But anyway, it's not mercury, so that's okay. And what'll happen is you'll read the temperature on these bulbs. It'll come up like that. And which one will give you a higher temperature of the 2 as you sling it around in the room? The dry bulb. And why will the wet bulb have a lower temperature? Because of evaporation. You know that from wet t-shirts and other things. You feel that cooling effect and you fan yourself. And so now, if somebody like a technician comes into this room, somebody says, I'm hot and stuffy in this room. They used to take out some device like this. Now it's all electronic. But they would sling it around, and then they'd pull it down, and they'd say, okay, I know the dry bulb temperature. Oh, it's 75 degrees F in here. And I know the wet bulb. Oh, it's 62. And they would tell how much humidity in the room. And built into this, there's a little scale right here. You put the pieces together, you slide the scale, and you can actually infer the relative humidity. When do you think you would walk into a room, sling it around, and the wet bulb would have the same temperature as the dry bulb?
100% saturated.
Very good. Here in Houston, after a rain shower, it's 100% relative humidity. It's saturated air. And there's no evaporation potential. And so there's no evaporative cooling on that wet bulb. So that's probably the most difficult concept on this page, the wet bulb temperature. And if you look in your heat transfer textbook, there's an evaporative cooling section, and they'll even show you, using the analogy between heat and mass transfer, how you can actually infer the decrease in the temperature. But people have already figured out, correlated it, and so you can look at the equation in your heat transfer textbook, but I don't have time to go into the details there. But what do we have here is another temperature. It's called the dew point temperature. So how many people have walked out in the morning in the spring or sometime and the grass is all wet, and they walk across it barefoot, or they walk across and their shoes are all wet? They get it true? Or maybe you go out and you think, did it rain last night, or why is my car all wet? My car's all wet, as I'm leaving in the morning. Well, it dewed out of the air. So during the day, the temperature was high, and then, this is the day, and then during the night, the temperature goes low, right? And then right around, 5, 6 a.m., right before the sun starts to come up, you get the lowest temperature. And what happens is the air cooled so much that even though it was very humid during the day, it became closer and closer and closer to being saturated air. And then finally, it was exactly saturated air. It cooled a little more, and it said, I got some excess water vapor in me. It's dewing out, and it just falls. Falls down, lays on the grass, lays on your car, lays on your roof, something. If you have a carport, or sometimes you'll see it's like, hey, it fell over here, but not over there. It's dry underneath. So anyway, that's the dew point temperature. This one we can work a pretty good equation out, because you say right here, I know the partial pressure of the water vapor actually right now. This is the actual right now in this room. And knowing that partial pressure of the water vapor in this room right now, I can tell you what the dew point temperature is of the air in this room right now. Oh, well, I don't have to cool it to that temperature to see it start to dew. I can infer that if I conceptually cooled it, it would dew at that temperature. So mathematically, it's maybe a little tricky, but you say, if I lowered the temperature to the dew point temperature, the saturation pressure would be exactly the actual vapor pressure. Does that equation, I hope, well, you have to struggle with it. I may make it a little too easy, or seem too easy, but again, let me repeat that. The vapor pressure in the room is something. In this room right now, it's a lot less than the saturation pressure for the dry bulb temperature in this room. But you calculate it somehow, and you got it. Then what you do is, conceptually, you lower the temperature, conceptually, until it hits a particular temperature called the dew point temperature, where the saturation pressure matches the room vapor pressure. There you go. You have to work with it in your own mind. Now, the easy ones are the relative humidity. Everybody knows the relative humidity. You see that reported all the time. Relative humidity is the ratio of the vapor pressure. Well, really, you go back to the definition. A mole fraction of water vapor actual to the mole fraction water vapor maximum. And then you say, well, what's the maximum? The maximum is going to be related to the partial pressure of the vapor actually to the maximum, which is the saturation pressure. And one more concept that I'll pick up next time is the humidity ratio, which you, as a budding engineer, will really, really like. But a lot of people don't use it in the vernacular. We talk about the relative humidity, not the humidity ratio. And it's the mass of the vapor divided by the mass of the dry air in our moist air mixture. Have a safe weekend. Thank you very much.